No, because I got it.
Okay, so here we go. Last time we were just finishing up the what you might call the material for Chapter 7, but there's some organizational ideas that I want to show you, this diagram business, and then we're going to do a bunch of examples today, the purpose of which is to show, in some sense, how to make use of these diagrams and how to use all the tools that we've been talking about to actually compute line integrals and surface integrals. Okay. We've seen this before, what I call the strategic diagram for R2. There are these different theorems in two dimensions, right? There's fundamental theorem of line integrals. There's a Green's theorem. They seem pretty different, but they're related and connected. So they're connected by virtue of the fact that this composition of their relevant operators is natural in a really sort of unexpected way. So what we call it, this is an exact sequence. So we've talked about this before, but any vector field for which Green's operator is 0, that is a gradient of some function, and for any gradient of a function, Green's operator is 0, right? So that's a connection between the two different operators. There's also this sort of comparison or analogy, whatever you might want to call it, that I like to represent by this little shorthand in the diagram, that if you take a function and look at the gradient field, if you take a curve and look at the boundary points, and if you sort of compute on each side, if you will, then the two results are equal. And we talked before about how, try that again, Green's theorem structurally, diagrammatically, exactly the same pattern. Right? So very, very similar theorems, even though on their face they don't particularly look all that similar. Okay. Now, there is a three-dimensional version of this. And now that we've talked about all the necessary tools and objects and ideas, blah, 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 we're ready to talk about this diagram here. For whatever it's worth, there is a slightly more fleshed out, slightly better spaced out, I don't know how you want to say it, but there's a little bit more elbow room, a little bit more room to move, a little bit easier to draw pictures and etc. Version of this diagram that I have on the Sakai site. Y'all can download this file. It's a PDF. It's in the resources section of the Sakai site. If I remember correctly, just the one for our sections. This isn't really course material. This is sort of my stuff. This is out of my textbook, by the way, for whatever that's worth. Anyway, this page you can download from the Sakai site. And I'm going to work off of this as I talk through the diagram because, like I say, it's a little bit better spaced out. Okay, so again, the pattern holds in terms of exactness. This whole sequence here is exact. In that, if curl is 0, then there is an anti-gradient. And said differently, if there is an anti-gradient, in other words, if you're looking at a gradient field, then in fact curl is 0. Not only is that true, but furthermore, it's true one notch over also. So all curls have divergence equal to 0, and if divergence is equal to 0, then it's a curl. Right? Regularity issues assumed, of course, and we're not going to get into non-regular stuff. So the same relationship in some sense, two different places on the diagram. So how about that for eyebrow raising? What are the odds? Surely this must mean something. I think that's really interesting. Okay, so likewise with the what I like to call the accumulation theorems. So if you take the gradient of a function, if you take the boundary points of a curve, and if you compute on either side, same result. And again, just like in two dimensions, same if you move over a notch. Stokes' curl theorem. Seemingly totally different statement. We're not computing change, we're computing circulation. It's not over a curve, it's over a surface, right? There's very big differences, but structurally very, very similar, very closely related. And then likewise, Gauss's divergence theorem. Again, the exact same pattern. Geometrically totally different, of course. So I think there's a lot of value in seeing how strong these analogies are. For one thing, having this diagram the way it is gives you a kind of what I'll call an organizational tool to sort of organize these ideas in your mind, rather than have all of your ideas about these things in some sense all disconnected from each other. Putting it all into an organized structure might make it a little easier to keep track of everything. Also, in some sense, notice now you don't really have to view these as three separate theorems. You can view these theorems as all being the same theorem. In fact, not just three, all five of these. 6 if you count the fundamental theorem of calculus in one dimension, right? All 6, in some sense, versions of this one theorem. You can understand just by understanding one pattern on this diagram. Now, you may be thinking to yourself, okay, well, yeah, but I mean, come on, this diagram's huge. I mean, what am I going to memorize the whole diagram? Actually, yes, and in fact, I'll betcha you may have accidentally, inadvertently already memorized a pretty fair portion of it. Because it's mostly patterns, right? In one dimension, wrong tool. In one dimension, we've been talking about vector line integrals. That's the only kind of one-dimensional integral we've talked about in Chapter 7. It's vector line integrals. That's it. In 2 dimensions, we have not talked about anything but fluxes. In 3 dimensions, we have not talked about, nor is there really anything other than triple integrals. So, what are we evaluating on these in these various places? Is well, what else could it be? And again, you can kind of, like I say, you've probably already accidentally memorized those. You do have to memorize the order of these operations. Okay, so that's not that bad. Grad curl div. Say that 10 times in a row, boom, you memorized it, right? So go ahead and memorize that. And with that done, these theorems, you don't really have to memorize all of this. You can just notice the pattern. Just remember this pattern, and applied to this part of the diagram, that'll tell you the fundamental theorem of line integrals. You don't have to memorize it. You read it off of the diagram. And then likewise in the other places for Stokes and for Gauss. All right, so there's one other thing I want to point out on this diagram, and that is how to view and how do the various facts related to the special vector fields. How do those show up? How do we talk about them in this context? The special vector fields I'm talking about here are the path-independent vector fields. Now let me show you several different ways that you can represent path independence on here. Well, on the one hand, every path-independent vector field is a gradient of something. They are gradient fields. They are also irrotational, namely the curl is 0. So now these are different properties, right? Being a gradient, being irrotational are different properties, but they are different properties of the exact same vector fields, again, assuming regularity. And then, of course, path independence itself, and here's how I like to represent path independence. If we have 2 curves with the same boundary points, then they give you the same value of the line integral, the vector line integral. So 3 different properties of the exact same vector fields. These are the ones I'm calling here the special vector fields. Now, keep in mind, if you have a gradient field, that means the vector field has an anti-gradient. That's what this is. This is the anti-gradient. And once you have that, that means that you can use this theorem. Right? So an alternative to path independence is just the use of the fundamental theorem of line integrals. You do have to actually find that anti-gradient, but nevertheless, that's an option on the table. And then now let me ask this question: where does this relationship come from? How do we know that curl being 0 is a giveaway of the vector field being a gradient? Well, we made an argument, the key tool of which was Stokes' curl theorem. All right, so bunch of stuff on the screen here about path independence and other related properties. So what about surface independence? And this is another reason I love the diagram. Here's how you represent all the same ideas of surface independence. You just slide it over one notch. All of the pattern holds. So let me just kind of walk through it. Let me just kind of highlight. These special vector fields that are surface independent, they're all curls. Divergence is 0 for all of them. Again, assuming regularities. They're surface independent. This is what surface independent looks like. Any two surfaces with the same boundary curves give the same flux. Now, if you have such a field, being as it is a curl, you could find the anti-curl, and if so, then you can use Stokes' curl theorem alternatively to surface independence. Furthermore, how do we make the connection between divergence being 0 and the vector field being a curl? We made that connection by way of an argument whose key tool was the divergence theorem. So the pattern, it's perfect extension of the pattern. Right. So again, a really nice use of the diagram, and I like to point out that if you are uncertain about some aspect of this, how would I make use of the divergence theorem, for example, to understand the exactness of this part of this sequence? Well, what's going on here, in other words? How does this fit into that? Okay, well, just, translate the question and look for, back in the notes, how did Stokes' theorem get used to help us understand this part of the diagram? And the roles are totally analogous. So you can use your understanding of something else to help you understand something that you might be focused on. Okay. All right. And with this diagram now discussed, I'm going to talk now about how to use this to help you compute line integrals and surface integrals. I got 6 examples. We probably won't get through all of them, by the way. I got through 5 of them in my first lecture today. The 6th one is a lot less interesting. It's pretty straightforward. But anyway, we're going to get through as many as we can, and I do have some recordings that I can point y'all toward if you want to see the remainder. Okay. All right, so here we go. First thing, when you're trying to compute a line integral or a surface integral, look at the diagram, identify where you are, and infer your context from the diagram. Let me show you what I mean by that. Here in this first example, notice we've been asked to compute a line integral. So we're going to identify a line integral in the diagram, but importantly also, notice our parametric curve that we were given. 3 components, right? That means this is in 3 dimensions. Likewise, the vector field, 3 components. We are in 3 dimensions here. So when I look at the diagram, here it is. Notice I'm looking in the I'm looking in the 3-dimensional diagram, and we are looking at a line integral. So this is my context. Notice line integrals show up as part of these 2 theorems. So everything that I should need relevant to the question of how do I compute that vector line integral should kind of come from, if you will, sort of this part of the diagram. Nothing outside of this part of the diagram should be relevant. Now I mention this because what will regularly happen when on an exam, final exam, what have you, is that the question at hand is to compute a vector line integral, and there will be students whose work includes computing the divergence of the vector field. There's no need for that. And one thing you have to keep in mind right? Keep in mind, the way papers are graded, we're not just going to look at the answer down at the bottom and see if it's right or it's wrong, right? We're looking at everything that's written that's not scratched out, of course. You disavowed it. It's like it's not there. But we're going to look at everything else that's written and infer from that how much are you understanding the problem, right? And if the question is about a vector line integral and you're writing about divergence and triple integrals, or you're making reference to Gauss's theorem, all of this stuff has no chance of being useful, right? And so it's what I'm going to call it's a bad look, right? It makes it look like you're not understanding the ideas and how they fit together. So you have to keep in mind, grading is a subjective thing. By the way, it won't be me grading the final exam. Just FYI, right? So those graders on the final exam are going to be trying to get some sense of how much does this student really understand. And when you write these things down on a line integral question, like I say, it's not a good look, right? So make a point, please. The diagram will tell you what to avoid talking about completely, right? If the question is about line integrals, steer clear of any mention on your paper of divergence or three-dimensional solids or triple integrals. Don't write the word Gauss down anywhere. Just steer clear of all that. Does that all make sense? Okay. All right. So, this is our context. This is our world right here. This is all we need to look at for this question. Okay, back to the question. Let's see. Compute the appropriate operator and the appropriate boundary and infer what that means. Okay, so back to the diagram. Keep in mind, this is all red. This is stressing me out. Let me put this in blue. Okay, we're in R3. We're looking at this. So we have a vector field and we have a curve. The diagram is telling you right here to compute the curl of that vector field. Let's go ahead and do that. Probably going to be useful one way or another. Also, think about the boundary of your curve. And one way or another, that's liable to be useful. Okay, so I'm going to, as I said on the previous page, do what the diagram tells me to do. Right? And then we'll infer appropriately from that. Okay, so here we go on this example here. Let's see here. It said to compute the curl. So we do that. The curl. Now, for whatever it's worth, my little hack, this is maybe just a me thing, but I like to write out part of the symbolic matrix that I know is used to compute curl. I just find this personally satisfying. And let's see, the computation of curl tells me I need to take the y partial of that minus the z partial of that, which gives me, let's see here, the y partial, okay, that gives me 0. How about that? Okay, cool. And then I need to compute the z partial, the z partial of that minus the x partial of that, which is 2x minus 2x, which again 0. And then let's see here, I need to compute lastly the x partial of that, which is 2y, minus the y partial of that, also 2y. So again, 0. So we've computed curl as the diagram suggested. And going back to the diagram, from the fact that the curl is 0, I can infer that there is an antigradient. That means that the fundamental theorem of line integrals is on the table. Right? There is an antigradient. The fundamental theorem of line integrals applies. That's an option for how I might solve this problem. Is everybody with me? Okay, now, proceeding along, what else am I going to do? I am also going to take my curve and think about its boundary points. Okay, well, let's see. Let's plug in 0, and I get x of 0 is, 0, comma 1, comma 1. Don't trust my arithmetic, by the way. I'm error prone on arithmetic. Let's see. Now we will plug in 1 into here. Sorry. And we get x of 1 is, let's see here, negative 1, comma, e to the 0 is 1, comma, and then e squared. Okay, what does this tell me? My curve starts and ends, apparently, at 2 different points, right? It starts at the green point, it ends at the red point. And what do I infer about this? This is not a closed curve. It's an open curve. This curve is not the boundary of any surface. Right? So, by the way, a nice little pithy kind of summary of the options when it comes to boundaries. Your curve either has a boundary or is a boundary. Pick your pick. One or the other. This curve clearly has a boundary. Therefore, it is not the case that it is a boundary. It's not a boundary of anything. Okay. All right, so back to the diagram. The curve has a boundary, right? And therefore, it's not the boundary of anything. Therefore, there is no anti-boundary surface. Stokes' curl theorem would require an anti-boundary. There is none. There is no application of Stokes' theorem to this example. How are we doing? Everybody with me? Okay, so all together then, fundamental theorem of line integrals is on the table. Stokes' curl theorem is not. I suppose I could brute force plug and chug. Just to be open-minded about it all, what would I think about brute force plug and chug? That looks like a horrifying nightmare. Right? If this is x, this is y, and this is z, then this vector field is crazy. Right? So nobody wants to do that. So brute force, unappealing. Stokes' theorem, not an option. What am I left with? Fundamental theorem of line integrals, basically the only remaining example, or only remaining tool. I guess you could use path independence, but fundamental theorem of line integrals is going to be great here. So all you got to do is take this vector field. We know curl is 0. That means finding the anti-gradient. It's just a matter of taking a few anti-partials, playing the game, making it fit. Plug in x of 1, plug in x of 0, subtract, right? Fundamental theorem of line integrals is a snap. How are we doing? Okay, and I'm going to let y'all fill in those blanks because we've done fundamental theorem of line integrals problems before. The point to this discussion here is how to diagnose what kind of a question is this. Is this what do I do? Which of the many methods we've studied should we apply here? And we came to the correct conclusion. We should use the fundamental theorem of line integrals. Okay, so I'm going to move on to the next example unless someone has a question. That's good. Yep. Well, because it's an option, right? It applies. I mean, I took the curl, I got 0. That means there is an anti-gradient, and that's what puts this on the table. Notice, in order to be able to use this theorem, I need to know this function f, which is the anti-gradient in question. So knowing that it exists is what tells me that that is an option. Yeah. Yep. Okay. Okay, let's look at the next example. Okay. So let's see here. Again, 3 dimensions. Line integral in 3 dimensions tells me I'm again here. That means that again, nowhere on the page are we going to discuss divergence or triple integrals or solids or say Gauss's name or anything of the sort, right? All that stuff is right out. No chance. Don't even think about it. Does that make sense? Okay. So, let's see here. We are then going to do what the diagram tells us. We have a given curve and vector field. The diagram's telling us to compute the curl of the vector field and to think about the boundary of the curve. All right. Will do. Diagram. So here we go. Let's take the curl of this vector field, and now this is just various partial derivatives. Turns out all of the partial derivatives here are easy. And to go through and think about it. I mean, you're going to have to take, for example, the y partial of that. There's no y's in there. Right? You will then be taking the z partial of that. There's no z's in there. And just because of what's a function of what, all those partials are immediately 0. So the curl is 0. That tells us, let's see here. It tells us because we got a 0 there, it tells me that yes, there is an anti-gradient. So technically, fundamental theorem of line integrals is on the table. Everybody follow? So I look back here, though, and I ask myself, okay, I could find an anti-gradient. I mean, there is an anti-gradient for this vector field. And the thing is, I really don't want to have to try and find it. Right? Because, I mean, just look at this vector field. If I were going to find the anti-gradient, this is not a bunch of polynomials like the last example. I would need to find an x anti-partial of x squared e to the x. That's 2 integration by parts. Oh, right? Nobody wants to do that. Y anti-partial of this? Well, it could be worse. It's still an integration by parts. But then a z anti-partial of that, we can't even do that. So, yes, there is an anti-gradient, but it's extremely inconvenient. And so even though technically, yes, the fundamental theorem of line integrals is on the table, it's, I can't really, I don't know, I'm not happy about what I would have to do to get there. Everybody see? All right. Proceeding along. What else does the diagram tell us to do? The diagram tells us to take our curve, think about its boundary. So back to here. Let's see here, the curve. Okay, there's the curve. I need to find the boundary, so I need to plug in t equals 0 into there. X of 0 is, let's see here, 0, 1, 1. And then I got to plug in t equals 1 into there. That gives me that x of 1 is 0, e to the 1, and then 1. Okay. Okay, so this given parameterized curve is starts and ends at the same point. How about that? Everybody with me? Let's draw a picture then of this curve. This curve here, it starts at the point we computed in green. The curve then goes around and does all sorts of weird stuff, and then it ends at the exact same point. So this is a closed curve. I've been asked to compute a line integral, but what was not given in the statement of the question is that this is a closed line integral. AKA, I've been asked to compute a circulation. Right? Now, going back to the diagram, because the boundary is 0, as in there is no boundary, right? It starts and ends at the same point. Because because that's 0, that means that there is some sort of anti-boundary surface. That means that Stokes' curl theorem is on the table. Now, seems like a bit of a horrifying circumstance for using Stokes' curl theorem. After all, this curve is a nightmare. And if that curve is a nightmare, that means that finding this surface is going to be a nightmare. So this is not looking particularly inviting, but I claim it's going to turn out to be actually kind of nice. But anyway, let me not get ahead of myself here. How are we doing so far? So we're pessimistic about the fundamental theorem of line integrals because finding the anti-gradient is going to be tough. We're pessimistic about Stokes' curl theorem because finding the anti-boundary is going to be tough. And it turns out, actually, both of those calculations are actually very straightforward. They're just downright easy. Let me show you how both of those calculations work out. First, we'll start with using the fundamental theorem of line integrals. And here we go. Applying the fundamental theorem of line integrals. This line integral here. Let's see, color choices. I guess I'll use purple. That line integral is going to be f of x of 1 minus f of x of 0. And again, tempting to say, yeah, but I can't do anything with this because I don't know f. There's too much annoying computation to be able to find f. But good news, it doesn't matter because these 2 points, let's see here, these 2 points are the same. So I'm computing f at some point and then subtracting the exact same function f evaluated at the exact same point. So this is immediately 0. I don't have to know f, as it turns out. How about that? Everybody see what happened there? With all the good fortune, right? It worked out really nice. Now, here's the other way you could do this. The other alternative is to use Stokes' theorem. We could say, all right, well, this is the flux of curl dot ds, problem being that our surface here, S, we don't know how to find that surface. It's a super weird surface, but what we do know is the curl is 0. Right? So the curl being 0 means that my integrand is 0. That means effectively I don't even really need to know what the surface is. Whatever that surface is, I'm integrating 0 over it. So that is immediately 0. In the same way that this is immediately 0, likewise this is immediately 0. So, yeah, take your pick, as it turns out. Yep.
So if it's a closed boundary, is the fundamental theorem of line integrals always 0?
If the fundamental theorem of line integrals applies, in other words, if there is an anti-gradient, then yes. And for exactly this reason, right? If there is an anti-gradient function, you don't even need to know what it is, as it turns out. If there's an anti-gradient, if your curve starts and ends at the same point, then you're plugging in the same point into whatever that function is. So, boom. Yeah. Absolutely. So let me point out something really nice about what happened here. These calculations that we did actually played a role twice. So the fact that curl was 0 was helpful in 2 ways. The fact that curl was 0 was helpful in that it told me that I could use the fundamental theorem of line integrals, but it was also helpful because it was the integrand in an application of Stokes' theorem. So this being 0 was useful twice. Everybody see what I mean? And likewise, having thought through all this stuff in orange was useful twice as well. Let's see here. So the fact that this curve starts and ends at the same point, for one thing, tells me that's what makes it possible to compute the left side of the fundamental theorem in a lucky break, and it's also what tells me that Stokes' theorem is on the table. Again, doubly useful. Everybody happy? All right. Moving along. Number 3. Okay, I'm going to start moving a little bit more quickly through the sort of the context part because we've talked through that a couple of times now. Notice we are in 3 dimensions. We're computing a line integral, so that takes us right back to where we had been. We're in the R3 diagram. We're looking at a line integral. We're going to take the curl of our vector field. We're going to think about the boundary, if any, of our curve. And so following those instructions, here we go. The curl, let me zoom in better. The curl of our vector field, a little bit of algebra there, it ends up being -1, -1, -1. And that's just a couple of partial derivatives. Y'all can compute that on your own. But importantly, not zero. So kind of bad news. We computed the curl. We got not zero. That means there's no anti-gradient. That means the fundamental theorem of line integrals right out. Don't even think about the fundamental theorem of line integrals at this point. There is no anti-gradient to find with which to use it. Is that cool? All right. So, fine. Too bad. All right, let's think about this curve. Now, this is not given parametrized, so I'm going to need to understand this in a different way. Close enough. Let's see here. We have you'll notice a cylinder here, right? A cylinder along the z-axis. So let me do this, like so. And then let's see, we have this plane here that's intersecting with that, and this is, I'm not going to try to draw this plane to scale because it's hard, and we're going to end up only needing qualitatively representative information here anyway. So let me just take a whack at it here. This is not perfect, but there's a plane intersecting it, and the intersection is, kind of like that. So there's our curve. How are we doing? Everybody's okay. All right, good news. My curve is closed. Just geometric inspection. The curve is clearly a closed curve. That means that there is a surface for which this is the boundary. That's also pretty clear. Here's the easy candidate. Of course, there's many such surfaces, but this is the easiest one to write down. So I've got an anti-boundary surface, and that means that Stokes's curl theorem is on the table, and we've got a candidate. We can use Stokes's curl theorem for this problem. Is everybody with me? All right. So, okay, well, I guess we could, but it's not clear that's going to be particularly helpful. If you look at the line integral we're looking at here, our line integral, if I were to rewrite this with Stokes's curl theorem, I'm going to call this new surface S, by the way. I can look at a flux of the curl dot ds. And how am I going to find that ds vector? Well, okay, I'm going to have to parameterize this surface. You can parameterize the surface. It's not the worst thing in the world. After all, the surface is a graph, right? Our surface is part of this blue plane. The picture makes that clear. It's part of the blue plane. The blue plane, you can solve for z. So you can use the graph parameterization to parameterize that surface. But then you got partials and a cross product, and then you have what in fact is still a double integral, even when you've got it all sort of cranked out. It looks a little tedious. So I tell you what I think the best answer is on this question. I think that the easiest way to solve this problem is just to plug and chug. I think it's the most direct way to do it. Let's talk through the plug and chug. Now, for that purpose, I'm going to slide most of this out of the way just so that we can have some space. But I do need my diagram down here, so I'm going to steal my own diagram. Okay, so here's our diagram. I don't need that surface anymore. How am I going to parameterize this curve? Well, notice, because of the cylinder, I know that x and y are doing something actually pretty simple here. And okay, this is going to be a poor drawing. I apologize. But my orange curve projected into the xy plane, clearly a circle. and I know how to parameterize unit circles. It's easy. Parameterizing unit circles is just cosine and sine. So my parameterization of my orange curve, the x coordinates are just cosine t, sine t. Everybody see that? Now it does leave the question of what is z. Turns out z is easy to find because you can see right here that any point on this blue plane, the whole orange curve, of course, is on the blue plane. Z is just negative x minus y. And I know x and y. So that means z is minus cosine t minus sine t. So we parameterize this curve. My vector field is not scary. My integral, if I were to plug in this parameterization, pull back through this parameterization on this integral, it's going to have some trig in it. But it's not really that scary, and frankly, I think this would be a little bit easier than doing it with Stokes' theorem. Everybody see my reasoning there? Okay. I encourage you to try it both ways. Right? Pull back through this parameterization. See how that calculation flows for you. And then also compute Stokes' theorem by parameterizing this surface as a graph. See how that calculation goes. See which one you like better. My money's on this one. Everybody's happy. All right, example 4. It's very similar with a critical difference, but very similar. You'll notice the exact same vector field, so I immediately know that the curl is -1, -1, -1. It's the same field after all. Let's see here. My curve is similar, not the same, but very similar in the sense. It's harder than it looks. There we go. Good one. Similar in that we're still looking at the same cylinder. We're still taking a plane cross-section of it. So I've got to think about how this plane cuts through that cylinder. And okay, it's a little different. I'm going to draw it. I'm going to try to draw it a little bit differently. Yes, I don't know, something like that. This again just needs to be qualitatively accurate. It doesn't need to be actually precise. But again, I have a kind of a tilted ellipse there. Again, it's clearly closed. That means that this is again clearly a boundary. Again, then Stokes' theorem is on the table. This time, Stokes' theorem is going to work out really, really nicely. Let me show you why. Here we go. Stokes' theorem applied here. I'm going to be looking at the flux through this surface of the curl dot the ds vector. Doesn't look too great right now. Let me rewrite the ds vector here. I'm going to rewrite the ds vector as unit vector little n times ds scalar. Right there's my ds vector. This little n, what can I say about little n? Well, on my surface, notice that my entire surface is actually part of that blue plane. The blue plane has an equation I can see right in front of me. That means I can write down this normal vector easily. That normal vector, just reading off the coefficients, 1, 0, -1. Now I've got to fix it. There's the question of plus or minus that I haven't addressed. This plus or minus depends on orientations, and okay, maybe we might have to worry about orientation. We'll deal with that when we get to it. But then I also have to make it a unit vector, so I have to divide by the square root of 2. So there's our unit normal vector, or at least the form of our unit normal vector n. And notice what happens when you plug that in here. I need more space. When you plug into here, plus or minus, still not sure about that part, 1, 0, negative 1 divided by the square root of 2, and then ds scalar. That dot product 0, boom, done. We don't have to worry about orientations. I don't have to parameterize anything. Immediately 0. So always be on the lookout for good fortune, right? Sometimes the geometry is, you just gotta love it. This is perfect. It's exactly what we need. Sometimes. What do you think?
Why is it 0?
Say again?
Why is it 0?
Yeah. Just looking at the dot product. So I'm looking at this dot that, temporarily setting aside there's a plus or minus we'll deal with later if we have to. Square root of 2, we'll deal with that later. But this dot product's immediately 0. So plus or minus of 0 doesn't matter. And the square root of 2 doesn't matter at that point either. Everybody yeah? Mm-hmm.
Why couldn't we find the normal vector for the previous problem?
Oh, yeah, you could. Yeah, totally could. The problem is that if you did that here, great question, by the way, the normal vector here would be, let's see here, 1, 1, 1, right? So we have plus or minus, we'll worry about that later, not sure. 1, 1, 1, got to make it a unit vector, so we divide by the square root of 3, and we plug that in here, you get dot, blah, 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 and it remains that I don't know what ds scalar is. And how would we figure out ds scalar? We'd still have to parameterize. And so this was, look, noble effort, right? To hope that we would get lucky and this dot product would be 0 and life is good. But since it wasn't 0, it doesn't really buy us much to do what we've done. In fact, arguably, we've made our lives more difficult here because the ds vector, to compute the ds vector, I just need capital N. To compute the ds scalar, I've got to take the magnitude of capital N, which, as it turns out, will cancel with this magnitude that I've just divided by. And so I'm just creating extra arithmetic. And this was, like I say, noble effort, but we got a dead end. Does that make sense? Anybody else? Good stuff. Okay. All right, let's see how much of number 5 I can get done. In 2 minutes. Wow. Okay. Well, you'd be surprised how much we can do in 2 minutes. First of all, R3 asked to compute a flux. New context then. Right? Now, we're over here. That means that this is our world. Right here. This is the only thing that could possibly be relevant. That means we're not going to be computing, we're not going to be trying to find anti-gradients, right? Don't even look at the anti-gradient of the given vector field. It's a bad look. Don't write f of b minus f of a anywhere on the page. It's got nothing to do with anything. It has no chance of being relevant, right? So leave all that alone. We see our options. Notice also, though, we're given more than just this vector field f, whose flux we're interested in. By the way, let me document that on here. In green. The vector field we're interested in, right, is there. But it says right here that f is the curl of this other vector field over here that I'm going to give a name to. I'm going to call that G, just so I can talk about it, right? So this says G, compute the curl, gives you F. And I'm going to represent that on the diagram over here by, well, G must therefore be here if when we compute the curl, we get F. So this is our given, right? Let me get rid of all this stuff we don't need to anymore. We're trying to compute a flux of a vector field where not only do I know that my vector field is a curl of something, I've actually been told what the anti-curl is. Right? The question did us a solid and gave us the anti-curl, which, by the way, I mean, that's really nice because we don't know how to compute anti-curls in this course. So this is huge information. So knowing the anti-curl allows for using the Stokes' curl theorem, if you'd like. Does that make sense to everybody? Real quick, and I know we are out of time, but I just want to point out real quick, because it's a curl, I also know that means that the divergence is 0. That also tells me that I could use surface independence. And I claim that surface independence would be another wonderful way to solve this problem. Take a look at the surface. What you'll find is that it has a really easy boundary curve, and there's a much more desirable surface with that same boundary curve. Okay, I'm going to give you all some recordings where in a past semester I've talked through all these examples in detail. I hope those will be useful. And see y'all on Monday. Have a great weekend.